So we revisit the chain rule here, and there's some different notations that can be used for this, and I think the more ways you can make sense of it, the better off you're going to be. So in particular, we're going to talk about this Leibniz notation, which we'll come back to at the end of this video when we start talking about trying to take the derivative of parametrized curves, a new idea. At any rate, first we have talked about the chain rule applies when you have a function inside a function. So the composite of two functions or the composition of two functions. So one way we can say to do this is to take the derivative of the outside function, leave the inside function alone, times the derivative of the inside function. So sometimes that serves us well. In other cases, other notations and symbolism may help us more so. So in an attempt to understand ways, if we talk about Leibniz notation, in Leibniz notation, we think of calling that inside function g of x just u. And so then our f of g of x becomes, and don't get your feelings hurt here, becomes f of u. So now when we look at this y equals f of u, then what we can do is say that this dy dx, because remember this u is that inside function is a function of x. So when we say f is a function of u and u is a function of x, that means that f is actually a function of x as well. And so we do this by saying dy dx is dy du times du dx. And you can think of it as it's okay to think of this algebraically and kind of looking at this like the du's. I wrote that wrong. Hold on. So this, I said it and I wrote it incorrectly. So it's dy du times du dx. So dy dx is dy du dx. So you can think of like these du's as canceling. That's a reasonable way to think of that. Okay, we'll come back to that and see how we're going to use this in a little bit in a different context. Sometimes, and maybe I should throw in here too, this kind of notation here also works, I think, very well when we're talking about taking the derivative of, say, sine of a function. Because then what we will do is say it's going to be the derivative of the outside function is cosine u, so you're leaving that inside function alone, and then times the derivative of the inside function. Notationally, that's very convenient to call that just cosine u du. So let's talk about the green example here. So an object is moving along the x-axis, so its position is given by x of t is cosine of t squared plus 1. So the velocity is, we know, the derivative of position, which we can either write as x prime of t or dx dt, either one. So we have a function, t squared plus 1, sitting inside another function, the cosine function. So we can take the derivative of the outside function. So derivative of cosine is negative sine. Leave the inside function alone, and then times the derivative of the inside function, and the derivative of t squared plus 1 is 2t. A little minor cleanup will bring that 2t to the front with the negative sign, and we'll get to negative 2t sine of t squared plus 1. If you remember last year, it was a big deal, and some of us struggled with it initially, doing these 3-link chains. Hopefully this has gotten better. So we can see a function 2t sitting inside another function sine of that, and that in turn is sitting inside of a third function, the tangent function. So we work our way from the outside in. So g prime of t will first differentiate the outermost function. I tried to use the example of an M&M with peanuts, where you were going to eat away the candy coating first, leaving the chocolate and the peanut alone, and then you'll eat away the chocolate, leaving the peanut, and then get to the peanut at the very end. So derivative of tangent is secant squared, and we leave the rest of that stuff alone. Then once we're finished with that outside function, we work our way inside, and so now we're going to take the derivative of 5 minus sine of 2t. So the derivative of 5 is 0. The derivative of negative sine of 2t, well, we'll hold off on the 2t part, but get the negative, and derivative of sine is cosine of 2t. And then finally, we'll get to that innermost function, the 2t, and its derivative is 2. So the 2 will join the negative and come all the way out in front as a negative 2 secant squared of 5 minus sine of 2t, and then times, now this is not in the secant squared at all, but we'll have the cosine of 2t. All right, we can even do, crazily enough, a 4-link chain. We can do this all day once we get the hang of it. So now we have a 5x sitting inside of a tangent, sitting inside of a sine, sitting inside of a 4th power. So the idea is you always work your way outside in. So differentiating the 4th power, we'll get 4 sine to the 3rd, leave everything else alone. Then we'll take times the derivative of the next thing we encounter is that sine function. So it's going to be a cosine of, and we'll leave the inside stuff alone. Now once we've worked our way past the sine, now we're to the inside of tangent of 5x. Derivative of tangent is secant squared. So that's going to be secant squared, leave the 5x alone, and at long last we make it to the 5x, and its derivative is 5. So I don't think we can do a whole lot with that. We can bring that 5 in front with a 4 and make that 20 times sine cubed of tangent of 5x times the cosine of tangent of 5x times the secant squared of 5x. Whew, crazy. Well, let's go to the next, see what we have in store for us here. So let's talk now. This is a new idea, something we've not done before, and that's why I have put the little asterisk by it there. So slopes of parametrized curves. So these are now these parametric curves we talked about a little bit before, and so they're given by x of t and y of t. So t is the parameter or the variable, and as you plug them into whatever functions we have for x and y, they will tell us the position of that particle at various values of t. So we say that the curve is differentiable at t if x and y are each differentiable at t. And at a particular point on the curve, where y is also a function of x, then we have a relationship between these derivatives, dy dt, dx dt, dy dx, that are related from the chain rule as written by the Leibniz notation. So the dy dt is going to be dy dx times dx dt. Here again, you can kind of see those dx's canceling if you want to think of that, and that's a reasonable way to think of it. Since we are trying to solve for dy dx, then we can divide this dx dt to the other side, and that will give us the dy dx that we want to find. That's going to give us, say, a slope of a tangent line, and that's going to be dy dt over dx dt. So let's see how that works in practice. So here's our example. We've got our parametric equations given by x equals secant of t and y equals tangent of t. And we're given a point, square root of 2 comma 1, and that point occurs where t is equal to pi over 4. We want the equation of the tangent line. So since we already have the point, what's left to find is the slope, and the slope is going to be given by dy dx, as it has before in rectangulars. So to find dy dx, we want to take dy dt over dx dt. So off to the side here, we'll figure out what dy dt is, And dy dt is going to be the derivative of tangent, which is secant squared t. And we're going to want to evaluate that at t equals pi over 4. So that means we're going to get 1 over, we're going to get cosine of pi over 4 squared. And the cosine, let's see, cosine of pi over 4 is square root of 2 over 2. Squaring that is going to make that be 2/4, or 1/2. And to divide by 1/2 is going to be 2. And so that is our dy dt. The dx dt, we're going to differentiate secant t, which is going to be secant t tangent t. And that also is going to be evaluated at t equals pi over 4. So that means we're going to get secant of pi over 4 times tangent of pi over 4. Well, secant of pi over 4 we said was 1 over the square root of 2 over 2. The tangent of pi over 4 is going to be sine pi over 4 over cosine pi over 4. So let's see, this to divide by square root of 2 over 2 is going to be to multiply by the reciprocal. And we know that sine pi over 4 over cosine pi over 4 is square root of 2 over 2 over square root of 2 over 2, which is 1. So we can simplify the 2 over square root of 2 to be square root of 2. And that is our dx dt. So we're getting there. Dy dx is going to be dy dt over dx dt. And we found dy dt to be 2 and dx dt to be the square root of 2. So if we think of 2 as being the square root of 2 squared, we get that the dy dx is square root of 2, which is our slope. Okay, we're almost there. We got our point and we've got our slope. So at long last, we can say y minus 1 equals the slope square root of 2 times x minus square root of 2, and that is our tangent line. All right, very good.